Dear learners, I welcome to this video lecture number 5 in Unit 2 Metrology of the subject Air Pollution and Control Engineering. In this video, we are going to discuss atmospheric dispersion. Atmospheric dispersion is the process by which contaminants move through the air and the plume spreads over a large area, thus reducing the concentration of pollutants it contains, the ambient air contains. The plume spreads both horizontally and vertically. If it is a gaseous plume, the motion of the molecules follows the laws of gaseous diffusion, which is called as atmospheric diffusion theory. The most commonly used model for the dispersion of gaseous air pollutant is the Gaussian model developed by Pascal, in which gases dispersed in the atmosphere are assumed to exhibit ideal gas behavior. The figure represents the Gaussian model. The principles on which the model is based are: the predominant forces in the pollutant transportation is the wind pollutants moves predominantly downward. The greatest concentration of pollutant molecules is along the plume center line. The molecules diffuses spontaneously from region of higher concentration to region of lower concentrations. The pollution is emitted continuously and the emission and dispersion processes in steady state. The figure shows the fundamental features of Gaussian dispersion model with the geometric arrangement of source, wind and plume. This is the figure which is called as Gaussian model, Gaussian dispersion models. It represents source, wind and plume. When we construct a Cartesian coordinate system with the emission source at the origin, the wind direction along the x-axis, the lateral and vertical dispersions are along the y and z axis respectively. As the plume moves downwind, it spreads both laterally and vertically away from the plume center line. As the gas molecules moves from higher to lower concentrations, cross sections of the pollutant concentration along both the y and z axis thus give the shape of Gaussian curve. Since stack gases are generally emitted at temperature higher than ambient air temperature, the buoyant plume will rise some distance before beginning to travel downwind. The sum of this vertical travel distance and the geometric stack height, the effective stack height. The source of the pollutant plume is in effective a source elevated above the ground at elevation z is equal to h, which are the parameters shows in the figure, and the downwind concentration emanating from this elevated source. These are the equations which used to determine the concentration of pollutants in a plume or ambient air in some point or a specific point. In this equation, Q represents the emission rate of pollution source. U represents the average wind speed in meter per second. Sigma Y represents the standard deviation of the plume in the y direction in meters, and sigma Z represents the standard deviation of the plume in Z direction. The units of concentration are grams per cubic meter. Since pollution concentrations are usually measured at ground level, that is for Z is equal to 0, the equation is reduced to 2. The above equation is reduced to 2. This equation. This equation takes into account the reflection of gaseous pollutants from the surface of the ground. We are usually interested in the greatest value of the ground level in any direction, and this is the concentration along the plume center line, that is for y equal to 0. For y equal to 0 condition, the equation is reduced to this equation. The main equation is reduced to this equation. Finally, for a source of emission at ground level, H is equal to 0, and the ground level concentration of pollutants downwind along the plume center line is given by. For the case of H is equal to 0, the main equation is reduced by this equation. For a release above ground level, the maximum downwind ground level concentration occurs along plume center line, which is following condition is satisfied, which is sigma Z is equal to H by root 2. The standard deviation sigma Y and sigma Z are measured of plume spread in crosswind and vertical directions respectively. Then we move on to dispersion models. Dispersion models are mathematical simulation or approaches made to dispersion of pollutants to study how air pollutant disperse in the ambient atmosphere. How the ambient air or the plume is dispersed near or above the ground levels. These dispersion models vary depending on the mathematical calculations used to develop the models. The dispersion models require the following details. The first one is very important: meteorological factors. About meteorological factors we are discussed in video 1. So it is an important thing to make a dispersion models, to develop a dispersion models. So 2, source of emission, where the ambient air is polluted or the polluted air is coming from, and emissions parameters. And finally, terrain elevation and the source of location. From what location the polluted air is coming from, like that. Types of air pollution dispersion models. The first one is box model, which is otherwise called as fixed box model. It is simplest type of model. It assumes the airshed is box shaped. It assumes that air pollution present in the box are homogeneously distributed, and hence air pollutant concentration is emitted with the airshed. It has very limited ability to accurately predict dispersions of air pollutant over an airshed. This figure shows the Typical fixed box model. This figure represents the downwind dimension, crosswind dimension, and vertical dimension, and wind direction. That means lateral wind direction, and the meteorological factor which is solar radiation, etc. Then types of air pollution dispersion models. The first and most important one is Gaussian dispersion model. It is most commonly used model type and one of the oldest. The pollutant follow a normal probability distribution used for dispersions of continuous buoyant air pollutant plume originating from ground level or elevated source. Primary algorithm used is generalized dispersion for a continuous point source. Yeah, this picture represents the Gaussian dispersion models, which shows delta H plume height with small h stack height and capital H effective stack height, which are discussed in unit video number 4. Types of air pollution dispersion models. Lagrangian model. Lagrangian dispersion models mathematically follows pollution plume parcels. In this model calculates the air pollutant dispersion by computing the statistics of the large number of pollutants plume parcels. It uses a moving frame of reference as the parcel move from their initial location. It is based on fluid element that flow instantaneous flow. The next type is Illyrian model. In this model, chemical species moves in fixed grid. It used numerical terms to solve equation of mass conservation of pollutant. It's difficult to solve the numerical framework in this model. Its advantage is well defined 3D formulation, which is necessary in some complex regional scale air pollution problems. The figure represents the basic model. Types of air pollution dispersion models. Dense gas models. Dense gas models are the models that simulate the dispersion of dense gas pollutant. For example, pollution plumes that are heavier than air. Thank you, learners.